Okay, so I'm really excited to be talking to you guys today. This talk is called What is Math For? Using mathematical ideas to make sense of the world around us. And for the first part of this talk, I'm just going to share some examples of how we use mathematical ideas to make sense of the world around us. And then for the second part, I'm going to share some ideas about how we teach this stuff. So I want to start with planetary motion. In the 16th century, our astronomical observations were getting good enough that we could see that planets weren't moving in perfect circles around the sun. They were actually moving in these sort of off-center ovals. And Johann Kepler studied these observations, and he determined that these weren't just any old ovals. These were actually ellipses. An ellipse is a precise mathematical shape. It has two important points on the interior known as the foci. And what Kepler discovered was that for any elliptical orbit of a planet, the sun was always located at one of the foci. It was also known that the further away from the sun that a planet was, the longer it took to go around. So if you measured the time it took a given planet to go around the sun and compared it to the long radius of the ellipse, you found that if you cubed that radius, it was always equal to the square of the time. So planets were following this very specific mathematical formula in terms of how long it took them to go around the sun. He also knew that planets sped up when they got close to the sun and slowed down when they were further away. So if this is a planet at 2 points in its orbit, you see that over the same period of time, the one that's near the sun has swept out a much bigger angle than the one that's further away from the sun. But those areas that have been swept out, Kepler found, were always the same. An imaginary line from a planet to the sun always swept out equal areas in equal time. So this was another sort of mathematical quirk that planets were following as they went around the sun. So these are some examples of mathematical ideas that are helping us make sense of the world. And these are purely descriptive, right? Kepler had no idea why these things were true. They were just these kind of funny mathematical coincidences. And then Newton came up with this mathematical idea. This is F equals ma, force equals mass times acceleration. And the basic idea here is that if you have an object and you measure all of the forces that are acting on it, so like gravity pulling it down or a contact force from something hitting it, or maybe a magnet pulling on it from over there, and you add up all those forces, and then you measure the mass of that object, and then you measure the acceleration that object goes through, you'll find that if you multiply the acceleration times the mass, it always equals whatever the force was. So these things are always in balance. And this is one of those things where once you know about it, you start kind of noticing it everywhere. Newton was able to apply it to planetary motion. He imagined that what was causing all these planets to orbit around was that there was a gravitational force field centered on the sun. And he came up with a mathematical description of that, which is given by this formula, where G is a gravitational constant, big M is the mass of the sun, little m is the mass of a planet, and r squared is the distance between the sun and the planet. And the r with the little hat on it just means the force lines are in the radial direction towards the sun. So if you plug this in for F in F equals ma, and you solve for the paths of the planets, you get the formula for ellipses. And more than that, you can actually derive from this all three of Kepler's laws. So you can see that we've actually made some scientific progress in going to F equals ma as a mathematical idea, because now we don't need to keep track of these individual things. We can just remember that F equals ma, and we can derive each of Kepler's laws kind of on an as-needed basis. So this is one of the things that a good mathematical representation gets us. It kind of reduces the number of individual things we have to keep track of. It reduces the number of things we have to memorize. Another good property for a mathematical representation to have is that it applies in many different contexts. So F equals ma doesn't just apply to planets. It also applies to falling apples or swinging pendulums or billiard balls ricocheting off on a pool table. So we know, for instance, that if we have a pool ball and we hit it directly with the cue ball comes to an abrupt stop and the other ball flies out of the collision. And we can actually use F equals ma to predict that that's what would happen. Here's a schematic of what that looks like. When the balls come into contact, the white ball is exerting a force on the red ball. And so if F equals ma, that means the red ball should be accelerating. Its velocity goes from 0 up to some amount. But there's an equal and opposite force from the red ball on the white ball. And this force is acting against the velocity of the white ball, so this should cause it to decelerate. And if we work it out numerically, we find that the balls don't come out of contact until that velocity of the white ball has gone down to 0. Now, we know that on a pool table, balls don't always hit each other directly. They actually take these glancing shots where they exit the collision at different angles and at different speeds. But we can upgrade F equals ma to work in 2 dimensions as well. And so if we know where all the balls are and we know the ball coming in, we can analyze a sequence of collisions. And in this way, we can use F equals ma to kind of see into the future a little bit. So altogether, this is just a really useful idea to have on your intellectual mantelpiece. You can kind of pull it down and use it anytime you need to figure out why Slinky is behaving that way, or how fast you're gonna have to drive the car to get over a ditch. You know, it's just this very useful general purpose tool for making sense of the world around you. But there's another thing we get from having a mathematical representation of nature, and it's that we can then shift attention to the mathematical equation itself and generalize it and try and find deeper insights. So let's go back to the pool table and let's dig into F equals ma and see if it can't tell us something else. We know that before the balls come into collision, there's no net force. And we know that when they are touching each other, the net forces cancel out. So throughout the entire collision, the net force is 0. Given that, we can apply some transformations from calculus and derive this equation. This might look a little scary if you haven't seen it before, but basically it's just a mathematically precise way of saying that the quantity in parentheses, mass times velocity, doesn't change. The combined mass of the balls times their velocity is constant throughout the collision. And we give that expression a name. We call that the momentum. And this is known as the law of conservation of momentum. So this gives us a slightly different way to look at the collision. Before the collision, that red ball is sitting there with no velocity, and therefore no momentum. The white ball comes in with some amount of momentum, which is fixed, and it transfers all of that momentum to the red ball, which then continues out of the frame, and the white ball, with no momentum, is stuck sitting there. Now, if you have a little more time on your hands, you can dig a little deeper into F equals ma and eventually uncover this expression, which again just says that quantity in parentheses doesn't change. And this is a slightly different quantity. It's 1/2 times the mass of the balls times their velocities squared. And this we call the energy. So once again, we can look at the collision in a transactional sense. The ball that's sitting there has no kinetic energy. The white ball comes in, transfers its energy to the red ball, and again, the red ball exits the frame. Now, it's important to understand that this is not the only outcome that would have conserved energy. For instance, the white ball could have just bounced off of the red ball and kept all the energy to itself, which would have looked really weird, but that would technically have conserved energy. They could actually split it evenly and go their separate ways a little bit slower, which would also look kind of strange. So basically, knowing that energy is conserved doesn't allow you to make a specific prediction. It just confines you to a specific set of outcomes. There are also a lot of different momentum-conserving outcomes, but if we imagine that both energy and momentum are conserved, then we need to find an outcome that's in both of those sets. And it turns out that there's only one, and this is the one that happens. So in a way, knowing that both energy and momentum are conserved allows us to make a prediction. The balls move in the only physically viable way that they can, which keeps both of those quantities conserved. And much as we could upgrade F equals ma to apply in 2 dimensions, we can also upgrade these conservation laws. And so this gives us 2 different ways of looking at the pool table. We can look at it in terms of F equals ma, or we can look at it in terms of conservation of energy and conservation of momentum, which in this case has to be kept track of both horizontally and vertically. So F equals ma is a series of analyzable collisions, but in the conservation law view, the cue ball comes in carrying an amount of energy and momentum, and the balls move around in the only way they can that sort of conserves those amounts. So these 2 theories completely coincide with one another. They don't disagree. So we can't really say that one of them is right and one of them is wrong. We just should choose the one that we find most useful. So F equals ma has some nice advantages. The idea of a force and mass and acceleration, these are all very intuitive ideas to us as human beings. So that theory deals with a lot of intuitive concepts, whereas the conservation laws rely on this idea of energy and momentum, which are these more abstract quantities. They can't be directly observed. They have to sort of be calculated. But But on the other hand, F equals ma is kind of a tricky framework to deal with. If you're trying to solve problems, you're generally going to need calculus in order to use F equals ma, whereas the conservation laws are stated in such a way that you can solve the same problems and get the same answers using nothing but basic arithmetic. And this trade-off is very common when you're dealing with mathematical representations. Often you can pay a sort of tax of abstraction up front, and then after you've done that, you get this great reward, which is that your calculations actually get a lot simpler. But there's another thing you get from a more abstract representation, which is you can often see deeper insights. This idea that there's this stuff called energy, once we became aware of it, we started finding it all throughout nature. So you have radiant energy from the sun that gets turned into chemical energy in a tree through photosynthesis, which then gets turned into heat energy when we burn the tree. And these are all contexts where F equals ma doesn't apply. So conservation of energy is not just some weird quirk of F equals ma. It actually turns out to be a fundamental law of nature. And it's one that we were only able to discover because we'd come up with a sufficiently abstract mathematical representation. And the other beautiful thing is that this process of climbing the ladder of abstraction doesn't seem to stop. Physics just keeps going through these conversions where about a century after the conservation laws were discovered, there was this new way of thinking about physics called the Lagrangian formalism, which is almost comedically abstract. Just to give you a sense of it, the main variable there is L, called the Lagrangian, and this is called the Euler-Lagrange equation. And if you wanted to represent a pendulum in this formalism, you would need to find the Lagrangian of a pendulum, which is given by this formula for L. You then plug that L into the Euler-Lagrange equation and solve it. And the solution doesn't give you a specific answer. It actually gives you a path through an abstract space. Each point in that path corresponds to a configuration of the pendulum, and the points are time-stamped, so this gives you a description of the pendulum's motion over time. So if this is making your head spin, just remember that this is just a really fancy way of saying F equals ma. But the reason we're going to this more abstract point of view is because we're getting these benefits. Believe it or not, this actually does make solving certain problems a lot easier, but it also gives us a much more universal view. It applies to a lot of different contexts. If you plug in this Lagrangian into the Euler-Lagrange equation, you get the motion of a pendulum. But if you plug in this Lagrangian, you get the theory of electricity and magnetism. And if you plug in this Lagrangian, you get quantum mechanics. It's almost like all these different subjects in physics are like different video game cartridges, and the Euler-Lagrange equation is like the video game console that you can plug them into and play with whichever one you want. And it gives us a kind of universal language for talking about all of these different branches of physics. But something to notice, I think, is that our notational system seems like it's starting to get a little out of hand. And I think it's important to recognize that this way of doing mathematics, where we write out these symbols and have certain rules for symbol manipulation, nature didn't give us this idea. This is what we came up with back when our only technology for representing these ideas was writing. So in a way, for the rest of this talk, I want to try and make the argument that mathematics is a beautiful set of ideas that suffers from having a very old, very bad user interface. It's really hard to learn this stuff. It's really hard to teach it. And we have lots of other interfaces now that we can try and use for that purpose. So I'm just going to grab one example, which is that there's a lot of these things around now. And these are little computers. So this activity of symbol manipulation, this is something these computers are capable of doing for us. So the idea is there a way to sort of let the computer handle all of this and then turn it into an interface where we can interact with these mathematical ideas in a more intuitive way? So this is a multi-touch screen. It has a few basic gestures that it'll respond to. One thing you can do is tap on it. So you can sort of touch any point on that surface and select a point. You can also drag. So if you slide your finger across the surface, the grid will keep up with you. And you can move your finger along any path, and the background will keep up. There's also scale. So if you take two fingers and spread them out, the screen will scale up and down. If you pivot your fingers around, you can rotate. And if you just freely move both fingers, you'll get some kind of combination of scaling and rotating. So these are the basic inputs you have with this screen. And so a question we should get in the habit of asking ourselves is, when we're looking at an interface, are there any ways to use these gestures to have a meaningful interaction with mathematical ideas? And I'm going to go through a pretty specific idea. And I think in the same way that looking at the specific example of F equals ma helped us identify some general principles in how we use mathematics to make sense of the world, I think looking at a specific example of an interface will help us identify some general principles in terms of thinking about different ways of representing mathematics. So the idea I want to share is a way of using these gestures to do basic arithmetic. So imagine we have a number line, and we're going to put on top of it an interactive set of hash marks. And there's a few different types of interactivity that these will support. One is you can select a number. So let's say I tap on the number 4. The hash mark below 4 will grow a little selection bubble, and in this way we can identify specific numbers. Another piece of interactivity is that the hash mark that's directly below 0 has a little button hanging off of it. So if we rest our finger on that button, it activates the slide mode. So now by sliding my finger back and forth, I can rigidly move these hash marks along underneath the number line. And in particular, if one of these hash marks has a bubble sticking off of it, that bubble will be carried along with the sliding motion. And it turns out that we can use select and slide to do a form of addition. So let's say I wanted to add 3 plus 2. Here's the procedure for doing that. The first step is to take the first number in our sum and use select to put a bubble around it. So we put a bubble around 3. And then to add 2, we're going to activate the slide mode. So first we press the green button, turning on slide. And we're actually going to put a selection bubble above that so we can see where it is. And to add 2, we're going to move this hash mark from 0 over to 2. And that moves all of the hash marks 2 units to the right, including our bubble, which started at 3. And it landed on 5, so that, in a sense, tells us that 3 plus 2 equals 5. When we release our finger, whichever hash mark is now below 0 inherits that plus mark. And anytime we want to add a number to something in our bubble, we just press the plus and slide it to whichever number we want to add. There's one other piece of interactivity. The hash mark under 1 also has a little button under it. And by resting our finger on that button, we activate the stretch mode. In stretch mode, the hash mark under 0 has a little anchor, and it's fixed in place. And if we slide the pink hash, this thing just scales up and down proportionally. And in particular, if you have a bubble on one of those, it'll be carried along proportionally by this stretching motion. So it turns out you can use select and stretch to do a form of multiplication. So let's suppose I want to multiply 3 times 2. It works basically the same way. We begin by selecting the first digit by putting a bubble over 3. And then to multiply by 2, we activate the stretch mode. And we have a selection bubble over it that starts at 1. And in order to multiply by 2, we just slide this over to 2. This has the effect of doubling the spacing between all the hash marks, and it sends our bubble from 3 all the way out to 6. So this is a way of showing that 3 times 2 equals 6. And when we release our finger, now if we've done multiplication, our hash marks are going to be all stretched out. So it immediately replenishes itself, and whichever hash mark is below 1 inherits that multiplication tag. So this is just another way of doing arithmetic. And so in some sense, we have 2 different systems here. One is abstract symbols and manipulation. The other is this sort of gesture-based way of doing arithmetic. To do it in the top one, we would just write the number 8. To do it on the bottom, we'd select 2 and then slide that over to 4 and get 8. So again, they totally agree with each other. It's not really a matter of which of them is right or wrong. It's a matter of which of these is conceptually more useful. And we know what we mean by useful. There are a lot of things we're trying to get out of a mathematical representation. One of the things we want is that it should reduce the number of things we have to have memorized. So let me ask you this. How did you know that 2 times 4 equals 8? It's unlikely you actually did a computation. You probably have that fact memorized. And in fact, you have several dozen of these multiplicative relationships memorized. And your ability to do multiplication generally pretty much depends on having this table committed to memory. On the other hand, with the gestural calculator, you don't really need to memorize anything. So that's one little benefit that it has. Another thing we're looking for in a representation is that it should apply in many different contexts. So let's consider fractions. In the notational scheme, knowing how to add integers doesn't tell you how to add fractions. You have to memorize some additional rules about adding fractions. So if you apply this in that case and reduce it, you'll find that 1/4 plus 3/8 equals 5/8. How does this work in our gestural system? Here we are zoomed in on the space between 0 and 1, and what we find is we can use the same gestures here. To add 1/4 plus 3/8, we tap 1/4, putting a bubble over it. We then activate the slide mode, and we slide everything over until that green bubble gets to 3/8. And this has the effect of pushing our bubble over to 5/8. So we've been able to accomplish addition of fractions without having to learn any new operations. What about multiplication? If we want to multiply 5/8 by 1/2, we need to learn this rule, and if we work it out, we see that that should be 5/16. So again, we can do multiplication gesturally using our same set of gestures. We have a bubble at 5/8, we activate the multiplication mode, and now we're going to actually be sliding towards 0 instead of away from it. So instead of spreading out, the hash marks are actually going to get bunched up, and this proportional shrinking is going to carry our bubble down to 5/16. So, there are a lot of different number systems we use. We use integers, negative numbers, fractions, decimals, and in the symbolic representation, we need to learn new rules in each of those cases. But our gesture system actually applies universally across all of those systems. So this is another kind of neat property that it has. But what we're really hoping for from a mathematical representation is that it puts us in a position to generalize and discover deeper insights. So let's try something. What we've been doing is picking points on the line and then using our gestures to find sums and products of those points. But here we're just acting horizontally on this line. We actually have on our touch screen the entire two-dimensional surface to work with. So let's expand this to a grid, and let's see if we can apply our gestures to points of the plane. So let's just pick 2 points, A and B. Can we find a point that is the sum of A plus B? Well, it's actually pretty easy to just apply our gestures again. The first step is to put a selection bubble over A, and then we activate the slide mode by pressing the plus sign, and now we're going to slide the plus sign up to B. And as we do that, this whole grid is going to move along with it, and in particular, it's going to carry that bubble at A along with it as well. So this is what that motion looks like, and you can see that our bubble lands at that point right there. So we can maybe call that A plus B. What about multiplication? Again, we can just put a selection bubble at A. We can press the times symbol and activate the stretch mode. And now the point at 0 is locked there, but we're going to slide that X up to B, and this whole grid is going to expand and now also rotate in order to accommodate that motion, and it's going to carry that bubble along with it. So this is what that motion looks like. That bubble lands there, and we can call that A times B. Now, we don't have any idea why we're doing this yet, right? What we're doing is we're paying an abstraction tax in the hope that it'll pay off later. But if we explore this two-dimensional arithmetic a little bit, we find that it's actually really nicely behaved. The commutative property holds, the associative property holds, and the distributive property still holds. And it turns out that what we've stumbled onto here is actually the arithmetic of something known as the complex numbers. The complex numbers are an extension of the real numbers, and they have a lot of applications in mathematics and in physics. And what I want to do real quick is stop here and just review how we normally introduce the concept of complex numbers to people. In algebra, after studying quadratic equations, we identify scenarios in which the quadratic formula kind of goes haywire and starts spitting out the square roots of negative numbers. We then call the square roots of negative numbers imaginary numbers, and we give the square root of -1 the symbol I and explore their algebra a little bit. We then say that you can take any regular number and any imaginary number and add them together to create something we call a complex number, and then we work out some general formulae for how to add and multiply complex numbers. So I have a couple of observations to make about this lesson plan. The first is that these are some of the worst terms you could have chosen. They almost look like they were designed to intimidate the student. The great mathematician Carl Friedrich Gauss even thought that the term imaginary number was unnecessarily confusing. He said that this subject, imaginary numbers, has hitherto been surrounded by mysterious obscurity is to be attributed largely to an ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, and lateral units, such an obscurity would have been out of the question. Gauss went on to make the problem substantially worse when he invented the term complex number. A complex number is not called that because it's particularly complex. It's called that because it's a mixture of a real and an imaginary part, a complex of those things, if you will. Which is just to say, we may not be presenting this idea here in the most flattering light. Now, there's a standard way of representing complex numbers in the plane. If you think of a complex number as a plus ib, you can think of a as the x-coordinate and b as the y-coordinate. So if we go back to this representation, if the coordinates at a are, say, ab, then we can associate that point with the complex number a plus ib. If the coordinates at b are cd, then we can attribute it to that complex number. Now remember, we used our gestures to identify that point as their sum. And if we looked at its coordinates, we would find that it coincided with the additive description for complex numbers. Similarly, we used our gestures to identify that point as the product of a and b, and its coordinates are also conform to the multiplicative rule for complex numbers. So what we have here is two different representations of the same mathematical idea. And again, what we're really looking for is which of these is more useful. And I think you can see now that what the multi-touch screen is doing for us is that it's allowing us to kind of cut to the chase a little more directly. We can get people into a position where they're computing with and exploring the properties of complex numbers without having to go on this big detour through quadratic equations, without having to make them think about the square root of a negative number, without even having to say the word imaginary. What we're getting to do maybe is take this idea of complex numbers off of the high shelf where we've been keeping it and maybe move it up a little earlier in a person's mathematical education. And I think there may be some real benefits to doing that because a lot of subjects in math and physics can be simplified if you know about complex numbers. So one example of this real quick is vector notation, which you're gonna have to learn if you want to do, say, electricity and magnetism. So a vector is a mathematical object. It's often represented as an arrow in the plane, which starts at 0 and is defined by the coordinates of its ending point. And to work with vectors, you need to learn two different ways of multiplying pairs of vectors. The first is called the dot product, which is given by this formula. And the second is called the cross product, which is given by this formula. And this one is especially interesting because this cross product actually comes in a right-handed version or a left-handed version. And we have all just agreed by convention that we're going to use the right-handed version. And you actually have to do this gesture with your hand to remember the geometry of that product. But if we just move these vectors into the complex plane, there are now some gestural operations we can use to make things a little simpler. Consider this type of product. What you can do is select the tip of A, putting a bubble there. You often want to reflect complex numbers through the horizontal axis, so you do that. And then you multiply by B, and you end up with this point. And the horizontal component of that point is the dot product, and the vertical component is the signed magnitude of the cross product. So you've taken these two operations and turned them into a single operation, and you no longer need to deal with the funny business involving the right-hand rule. You can encounter similar improvements in the affordances of things like geometry, algebra, trigonometry, and calculus if you can come at these ideas already knowing about complex numbers. In fact, the fundamental theorem of algebra is only even true if you're using complex numbers. So altogether, this seems like a good thing to have in mind before you start coming into contact with these more advanced topics. But I think there's even yet another reason why it's good to know about complex numbers, which is that if you know about them, it gives you access to a lot of the finer things in mathematics. A lot of wonderful mathematical objects live in the complex plane. My own pick for most interesting mathematical object is something called the Riemann zeta function, which is kind of a landscape in the complex plane. If you've ever seen fractals like the Mandelbrot set or the Julia set, these are diagrams in the complex plane that are they're basically these infinitely intricate like feedback patterns we get when we apply quadratic transformations over and over again. You can use complex numbers to parameterize hyperbolic geometry. And if you apply the Pythagorean notion of distance to the complex numbers, you get this weird mini version of special relativity. So you can actually have an interactive space-time to play with. And I think this list could be made really long. Well, the point I'm trying to make is just that there are a lot of things, a lot of ideas that we think of as being somewhat advanced, and I think these things actually come within conceptual grasping distance of a person who has had some introduction to complex numbers. So, all I actually did here was pick some interface we have around these days, multi-touch screen, and a specific concept that I thought I could represent on it, the complex numbers. But there are lots of different media and interfaces out there, and of course there are a lot of different subjects we would want to teach. And there are a lot of great ideas like this floating around out there. And I think the more of us that are trying to mix and match these ideas, the better. But basically, we have specific things in mind we want to accomplish by re-representing our subject. And I think the goal here, I think, is well captured by this quote by the mathematician M.F. Atiyah. The aim of theory is to systematically organize past experience in such a way that the next generation, our students and their students and so on, will be able to absorb the essential aspects in as painless a way as possible. And he goes on to say that this is the only way in which you can go on cumulatively building up any kind of scientific activity without eventually coming to a dead end. And I think this is the challenge of what we should be trying to do as educators, and I think the adventure of what we're trying to do, which is that we get to look at all these different types of media that are in our lives and look for ways to communicate our subject more clearly and more powerfully. And that's the talk. Thank you very much.